Okay, hello. I am Sophia Skiba,
I'm Kira Porter.
and we're from Benjamin Franklin High School in Queen Creek. We're very excited to do this. It was way more fun than I imagined.
Yes.
Yeah. So, yeah, we started off with kind of like printing up some background basically of what's going on, and like, because basically with the Moon 101, it's a bit harder to like know what's going on if that makes sense, because a lot of things just, oh boy, I'm trying to put everything in words, but like I kind of like start with the geological history, because then we could better understand kind of like the observations that we're making. So basically, about like 4.5 billion years ago, like the moon came to orbit Earth. We still don't really know how. There's about like four like kind of like main theories that are very popular, which are the capture hypothesis, fission hypothesis, the double planet hypothesis, and the giant impact theory. We still haven't like proven any of them, but yeah. So we're trying to like explain the origins, and the moon is like what helps is like the moon is geologically similar to Earth. It's like we've like found like mineral composition like contain like moon rocks that like we found on Earth too, and it used to have like active volcanoes and lava fields, which means it might have actually had like used to have active tectonic plates, but now it's kind of like just a wasteland today. So yeah, that's where we're at.
Um, we noticed in image one that since it has similar composition to the Earth, um, we used like yeah, uniformitarianism. We noticed that the craters were a result of asteroid crashing. And then all the materials in the photo or in the moon basically is like Tycho, all these different materials that could have made the craters and the divots in the moon be different because of the materials of the moon. Some of the craters are bulging and seem bigger, but some are very small and like they're just specks. There seems to be like bulges, which could be mountains, and they usually have like a shadow and like a light side to them. So that's like the upper right one. That's like the second one to the left. It has like like a white shine on it, so it could be a reflection from the sun, and then it does have a bit of a shadow, so it could be like a small mountain. Um, and This piece of the moon seems to give us to be smoother than any other photos we were given. So this shows that some of these crater crashings could be really old and ancient, and this area hasn't been impacted for a long time.
Yeah. And then with the second image, and kind of like, I don't know, what I was saying with like the second image, as same with the first image, as she said, it always seems to be like smoothed out. And though I think that might just because we're, looking down from a bird's eye view. But yeah. So image two appears to be like a dark radial fault. And it's like beside kind of like this, it's basically like along this line and kind of like the lighter gray area right along the dark fault is kind of like this ridge of just like kind of like moon debris and dust that's kind of been built up. But that was kind of hard to see at first. And I'm guessing that this used to be like a lava flow or a stream that appears to like have flowed from like a lower altitude from like I don't know, like some fault or like somewhere higher up that it's not that is from an origin place that's not on the picture, and it kind of like flow down into this like big kind of like whiteout plain, kind of like in the area where all of the white dust is collected. And I'm assuming that the area that the ridge and the area to the left of the fall are on higher planes than the rest of the surrounding area. Not too high because it's the moon. It doesn't really have that big difference in elevations, but it definitely is higher than the surrounding area. And the bulges that are just kind of like speckled all around the images, I'm assuming that they're piles of like mineral or moon rock or like just debris. I doubt that there's like really any like major crater impacts. There seems to be like a few like small like speckles of like crater impacts, but those must become like from like pieces of asteroid that like, fell off of the comet. And then for image three, I actually really like this picture. It was very pleasing to see. So image three is a fault line that formed from like when the moon was still forming. That's what I'm gonna guess, just based off of one, how rocky the area is, and also the clear fault line, like just how like pristine, no, not pristine, like how just clear and easy to observe that fault line is. I'm guessing it's one of the major fault lines of like if there had been any tectonic plates. And it's surrounded by like mountains, which I'm assuming are just like debris and moon rock piled on top of each other. And there's not that many craters in the area. There's like one big one and like a few small ones in the corners. So I'm guessing this area has not been hit that much, that often, unlike the others. And I'm assuming that like due to the round or like soft like appearance of like the crater's edges, like these craters were made like long ago. So like they're super old, and this overall area again has just not really been disturbed. And the majority of the land appears to be at a very low level, especially when compared to like the light gray shades of the tops of the mountains. And that's what we just kind of observed. Is there anything you would like to know?
Okay, thank you. So the first thing I want to say is I absolutely love this background and slide background and the one you had on the first slide, your very first intro title slide.
Thank
Just
you.
get that out of here. A couple of kind of aesthetic things. I guess I'll just say up front and get out of the way. So the font that you used, like when I'm looking at it right here, like I can read that just fine. But like on the first slide, some of the font in some of the lowercase letters anyway is kind of like the T, for example, is hard to read.
I see.
It just looks, so it's just kind of distracting. So anytime you're going to have any kind of text on a slide, just use something real basic, like, you know, Arial or Times New Roman or
like fans. Oh,
I guess, I don't know. Anything that's not too curvy or fancy or looks cursive, just something that's nice and neat. You know what I mean? That's really easy to read. Now go ahead and leave your.
Oh.
Okay, are we ready for the next one?
Yeah.
Oh no, go ahead and leave your moon slides up.
Oh.
Okay.
Oh no, I got some questions for you. And while you're getting another thing I'd say is when you have slides, you want people to be able to pay attention to whatever you want to use a slide to convey something important. And if it's full of text, people will start reading that text and then not necessarily pay attention to maybe what they should be paying attention to, like an image or a plot. And if they're reading, they're not listening to you either. And so you may say something that's really important that's not necessarily in your text, and they're going to miss it. So when you're presenting, and this is especially easy to do when it's virtual like this because nobody can see it, you know, I wouldn't put a lot of text, any more text than is absolutely necessary on a slide, and then just have like some notes there with you that you can look from.
Okay.
So go back to the very first picture. Yeah, there you go. Oh, okay. And in this slide before, you did a little, you know, kind of breakdown of understanding of the moon's formation. The one thing I'll say about that is, so we included things in the readings about those four different kind of ideas for the moon's formation. But what I'll tell you is of those four, there is only one that you will hear any studies related to anymore, and that is the giant impact hypothesis. All those other ones have a number of problems that since the ideas came up have basically thrown those out the window. So while there is still some things that we don't understand or we can't quite fit to get the moon the way we see it, the giant impact hypothesis in general is still the best explanation we have. But there are certainly details within that that they're still being worked on. So anyway, just put that out there. Okay, so my first question here, it's the second sentence. You say the moon is made of, and you list off a bunch of names. What are you trying to say? The moon is made of those craters?
No, it's just made of like materials that could like change the effects of crater. impacts.
Okay.
Like,
Okay.
like the materials and layering of the moon, like the different, not chemicals, but the different composition of the moon that could like cause the, like if an asteroid were to crash on the moon, if it made it bigger, or if it like just had it stay like in a very rocky like form, and it like those different materials and composition could change how craters impact the moon overall,
and how it like kind of like deals with kind of like how it deals like with erosion, if that makes sense, because like
I'm sorry.
But yeah.
Okay, so all those names that you list there, Tycho, Aristarchus, Kepler, Pytheas, those are all crater names. So those aren't like names of, you know, rock types or anything like that. So I was a little confused by that, but I see what you're saying. But yeah, those are just names of craters. But you are correct. How an impact crater forms, and what it looks like after the formation process is over, it is affected by the composition of the surface. You know, whether it's a hard surface, or if it's I mean, the moon doesn't have sand, but if it's a sandy surface, yes, that kind of thing does certainly have an effect on what happens, on how a crater forms. But in this particular image, yes, these are all impact craters. In this, every round thing you see in here is an impact crater. There are any volcanic features. The only volcanic feature, if you will, is the fact that all of these craters are on solidified lava. So this is on one of the mare. One of the questions I asked in that pre-survey you took about the moon and the moon's geology, what are kind of the three main types of features that you can see when you look at the moon?
Usually kind of like, it's like Maria's.
Okay, yeah, Maria, yeah.
Maria. I know there's like the higher level, different. Can you hear me out?
Mm-hmm.
Okay, and then there's also like craters.
Right.
No, I'm blanking. It's like the higher terrain or something. That's like, because the Maria, like I know how to explain it. I just forget the name. It's
that's fine. No, so there's Maria, and that's all the darker grayish areas, which are mostly found on the near side of the moon. There's a few areas on the far side, but for the most part, they're on the near side. That's actually something scientists are still trying to figure out. And then the highlands, which are everything else. Everything else is the brighter colored. And then of course craters, like you say. So those are kind of the three main things that you can see just looking at the moon, especially without a telescope. So in this image, we're seeing a section of Maria. Okay, so this dark, solidified lava due to volcanism. So there's a piece of information that I didn't give you for this picture, or even for the other two pictures, that would actually be very helpful for anybody looking at these pictures and trying to understand what you're looking at, especially if you're trying to figure out if you're looking at a impact crater or a volcanic feature. Do you have any idea what that piece of information might be?
I don't know, maybe oh no, we already know what side it's on. I'm blanking.
That's okay. So if I had given you the direction the sunlight was coming from, then you would know. So for example, in this image, the sunlight is coming from the left. So if you knew that and looked at any one of those round features, you could see, well, if the sunlight's coming from the left, and if it was a mountain, what side of that mountain or volcano or hill, what side of that would you expect to be lit up?
The left side.
Exactly. So if I had told you the sun's coming from the left, which it is, and all those objects are lit up on the right side, then that means it's a depression if it's lit up on the opposite side of where the sun's coming from. Now, how much? Now, in some of them, you can see some of those craters, you can see a lot more of the bottom of it. And some of them, you really can't see any because almost the whole bottom is shadowed. That has to do with how deep the crater is. So the relatively larger one in the upper right, where you can almost see the whole floor of that crater, that's a pretty shallow crater, and that crater has been filled in by other impacts that threw dirt into it over time. And then that one there, kind of to the left of there, it's mostly dark. So that's kind of the same thing, but it's really got a lot of stuff thrown into it. And sometimes also you pointed out a smaller crater that has a few of them have these brightness all the way around them. And yeah, that's of course sunlight reflecting off those rocks, but those are rocks, that's material that's been brought up from the subsurface, that's just a little bit brighter. And that gets into this idea of, and I don't think this was in the readings, if I remember. This is this idea of how lunar regolith can be, how mature it is. So the longer that lunar regolith or a rock is sitting on the surface, the darker it becomes from being exposed to radiation from the sun. So anyway, that wasn't in there. That's not so important for our purposes here today, but just want to put that out there. Okay, next picture. Okay, so again, this is a case where the sun in this image was almost directly overhead. So there is hardly any shadows. But you're right, with that thing you see right there in the middle, that is called a lava tube or a lava channel. So lava once flowed through this at one point way long ago. And what happens, so this is what was called a rill. And this is just one particular section of a rill. In the readings, it discusses rills and lava tubes. Do you recall how those form, the formation of those?
Oh no. Is it basically like lava like seeped up, if that makes sense, from kind of like when the moon was like a bit more geologically active?
Okay, so that is a way to explain how the mare formed. Yeah.
Oh.
So when the moon first formed, and then when it completely solidified, when it was no longer completely molten, and it was all solid, it looked just like a big ball of that brighter white material, anorthosite. And then eventually these big, huge rocks started coming in and nailing the surface and making these really big, huge craters or basins. And then that weakened the surface. So then the magma underneath the surface was then able to punch its way up and then fill in those big basins with lava. And then which then later solidified. And we now see those as the mare. So in this case, so during that same time, I mean, in that same time when that lava was coming out and filling the basins, there wasn't just one eruption of lava. There was multiple eruptions over time. So in this case, you would have had lava near the surface and flowing underground. And as it did that, or it came up to the surface and was flowing, as it did that, the stuff at the very top basically solidified really quickly because it was just exposed to space and it doesn't keep it warm. So the top solidified and the lava underneath that kept flowing. Okay, so basically it kept, and then once it stopped flowing, it left this hole down there, this tunnel. And then over time, that top part that had solidified collapsed. So if you could look down into the bottom of this rill, this feature here, it would look really jumbly. Lots of rocks and boulders and debris down there. Um, so anyway, that's that. And there are some impact craters in there. They don't look very round, but that really has to do with the just a horrible lighting condition in this image. So, okay, next picture. And yeah, I love this picture too. I absolutely love this picture. There's so much going on. There's so much geology in here, so much to talk about. So yes, there's another rill. Now be careful, it's not a fault. So a fault is something that's very specific, and that's a situation where the ground is either stretched and pulled apart or has compressed, and like one side of it has gone up over the other side. So that's a fault. But this here isn't a rill. In fact, the rill that runs through the middle of this picture, this is a zoomed out view of the same rill that was in the previous picture.
Wait, like how zoomed out?
So that the bend in the previous picture, that's the bend you see kind of in the top of the rill right up against that mountain.
Well,
You see that?
yeah.
Yeah, that's the same area that's in that other picture. So the second picture is just zoomed in on that area. So this is, and so just to the right, I guess in this case it'd be to the east of that particular area, that's where the Apollo 15 astronauts landed. So that was the fourth mission to land astronauts on the moon back in 1971, I believe. So this is an Apollo landing site, which is pretty cool. And they went there specifically because of that rill and because of the diversity of geology here. So that's an old lava tube that collapsed. It's called Hadley Rill. I'm not sure why they named it Hadley, but that's Hadley Rill. The bigger crater in the middle is called Hadley Crater. That rill then, of course, is just cutting through Mare, just like we talked about in the other picture. And then those brighter areas around the edges, that's all highland material. And the darker stuff, kind of weaving itself in and out of there, that's all Mare material. That's Mario, or Mare. I believe Serenitatis, I think, is where 15 landed. Anyway, yeah, lots of geology here. So here's a question. I want a question for this one. So we see the highlands, we see the Mare, we see the rill, and Hadley Rill and Hadley Crater. Those are the kinds of prominent features, the four prominent features in that picture. Can you rank those four features from oldest to youngest?
Oh, okay. Oh man, I gotta use my brain. Okay. So
Would the reels be first?
no, those would be, I think, like those would be after the Highland and the Maria.
Okay.
Except I can't figure out. So the Maria's all kind of like that. What's left over from the lava? But I think no, it's the Highland that's first, then Maria, then the rills, and then I think the crater. Then
That's just four. It's four.
four.
Yeah, it's four.
Oh, isn't there five?
You said four, I think.
Four.
Oh, okay. So I think like from oldest to like youngest, if that makes sense, is like the Highland, then the Maria, then the Hadley Rill, then the Hadley Crater.
Okay. And why do you think the crater is younger than the rill?
Oh no, I'm kind of like looking from like kind of like how, just if this makes sense, kind of like crisp and defined that crater is. It looks like, I don't know, it just looks like very like kind of like clean and like crisp, and it just, I don't know, kind of like looks like, kind of like, say if you kind of like put your hand in like snow and like punch the snow, then like it would appear like very kind of like very kind of like a very clear and pristine hole, and also it's on top of the rill.
Okay.
It looks
Yeah.
like, yeah, it's like cutting through the rill.
Yes. Okay. Yes. So your ranking there is correct. And yeah, that is a very nice fresh crater relatively speaking. But what really gives that away is the fact that it's overlapping the rill. So good job. Very, very well done. Good job. Okay, let's go ahead and go on to your asteroid presentation.
So this is the Asteroid 101 presentation that we made. So a little bit of the history of asteroids. There's no definite answer as to how asteroids formed, or how they kind of were part of the formation of the universe. There's some theories like how they're like chunks of different planets that were broken off in different, I don't know, formation episodes where planets would form together out of different rocks and different things. But the asteroids are kind of made of, they seem like they're mostly rock and debris of possibly other planets, with like space dust from different, colossal events that of formation. In the last decade, discoveries in different like exploration of asteroids have taken so that not only scientists can see them, but then satellites can see them that can survive, the journey and follow these asteroids to see them, either them moving or in orbit, if that is possible, or whatever. The majority of these asteroids are just floating in our solar system, and again, they could be remnants or are remnants of the solar system's formation from millions of years ago. They are sometimes like confused or assumed to be, like I said earlier, pieces of shattered protoplanets that failed to actually form into an actual planet. So yeah. In image 1, it's not a definite circle. It's more like an oval shaped image, and the top and bottom, when I was looking at this image, the top and bottom, like towards kind of the middle, are kind of smoothed out, and that could be like from it breaking off, and those sides were kind of smoothed out by other rocks, or just could be, I don't know, could be something that happened that caused the smoothing to happen. There's also seems to be like chunks of rock, like there's bigger chunks and then there's smaller chunks and then there's the space dust. But there are some chunks that seem to be a part of the asteroid, that are kind of sticking out and seem to be older and not like space debris and space dust. Once again, this could be a chunk from a broken planet or unformed planet in theory. Since this asteroid is not technically a circle or round, like other asteroids generally are, once again, it signifies that this asteroid is probably a broken piece of a larger asteroid or even like a small planet. Bigger chunks of the rock, like I said earlier, seem to be a part, but the smaller rocks are broken up, or there's just rocks that are just not broken up, and then there's space dust. This could also be a result of a large like planet quake or earthquake or collision, if that's possible. And then in image 2, the image that is shown to us appears to be kind of more smoothed out than any other crater. There's no definite like rock sticking out like the image before. It's more smoothed down, and there seems to be tiny like craters like this crater or this asteroid I mean is pretty big and could allow other asteroids to like fall into it and collide with it, but it wouldn't break at all. And it seems to have multiple like crater impacts, like they seem like pretty big crater impacts. And then there's smaller impacts and like medium-sized impacts as well. And the asteroid seems to be facing, like at the bottom of the image, it seems to be facing the sun or a source of light. Once again, this could be a chunk of space debris from the late stages of the solar system's formation.
And image 3, I did not like. So the image appears to be like very, very zoomed in, and the ground, I don't think like we're looking at the kind of like the asteroid surface, if that makes sense. Well, like we are, but like not the surface, because it appears to be like just coated in like a whole bunch of like space dust. Like all the rocks like seem like very fuzzy, and I don't know if that's just from the photo or if that's just from like the amount of like space dust just covering it. And the nodules in the picture are not craters, and the surface is, I don't know, at least in this low part, it seems to be very smooth. Like there's a few like kind of like loops, like divots, but other than that, it's all really smooth. And I'm assuming that this is kind of like one of the bigger asteroids, because usually bigger asteroids are a bit more smoother, and like I'm gonna assume that this is also circular in shape. I do not know, and because I just cannot confirm this because there's no scale of measurement. And based on the shadows of the rocks, the asteroid appears to be heading towards the sun, or yeah, just like heading towards the sun, I assume. If that's, but then again, it all depends on the satellite's like view position of the camera. So who knows? It might just be going, it might have its sun at its right or left. But yeah, that's pretty much it. Question.
Okay, thank you.
What happened?
So asteroids, as you probably realized, are difficult, if you will. That first image, so that's an asteroid called Itokawa. But a spacecraft was sent to the Japanese Space Agency, sent a spacecraft there in 2005, I think, or 4, something like that, and got a sample of it and brought it back. Some of it. So yeah, this is what we believe is called a rubble pile, where it's basically just a bunch of rocks and regolith just kind of stuck together. Just gravity is kind of keeping them together. This actually may be 2 different asteroids that are stuck together with a bunch of other bigger rocks or boulders, and then other rocks all the way down to the size of regolith. When I say regolith, you know what that is?
No.
Okay, so regolith is just a term that refers to very small, basically dirt, if you will. So on Earth, we get dirt basically from the bedrock, just rock that gets broken down into smaller and smaller and smaller pieces by wind or water, or plants can grow in between rocks and break them up, right? We typically on Earth call that soil, The only problem with using the word soil on the moon or Mars or any other planetary object is that soil implies there's some kind of organic material in it that allows, things to grow in it, for example. So regolith is just a term that's used to talk about fine-grained or small dirt, basically, materials on the moon and asteroids. So anyway, yeah, we don't really know exactly how asteroids formed because a lot of asteroids are probably just chunks of other things that have gotten stuck together. Where are asteroids found in the solar system?
Like the belt.
Yeah.
Or
I'm sorry, say it again.
oh, kind of like the asteroid belts, like between Mars and Jupiter, like Pluto, or yeah, or they could be. Maybe they could be from like beyond our solar system, like pretty far asteroid. I don't know.
Yeah, so they're in their own orbits, like planets are. The asteroid belt, you said, they call it the main belt, which is between Jupiter and Mars. There's also asteroids that share an orbit with Jupiter. They're called Trojan asteroids. And there's a group of them that kind of follow Jupiter in Jupiter's orbit, and there's a group that are in front of Jupiter in its orbit. And what's interesting about those is there's actually a spacecraft on its way now to study 7 of those asteroids. It's called the Lucy mission. So that's pretty cool. And then there's other asteroids that are in orbits that actually take it around the Earth. So there's the main belt, which is where most of them are, but then there's also these other belts of asteroids out there. It's a big mess, so to speak. Go to your second picture, and that is a picture of not Venus. That's a picture of Vesta. So Vesta is the second largest asteroid behind Ceres. Ceres is actually was classified as a dwarf planet a number of years ago when they went through that whole rigmarole. So Vesta is a relatively large asteroid. It's probably its own thing. It's not a collection of other asteroids like Itokawa is. And in fact, other than meteorites that we have identified as coming from the moon or Mars, the only other object where we're pretty confident we know where meteorites came from is Vesta. And those meteorites are called Vestoids, I believe is the name of them. So that's another interesting thing about Vesta. And yes, Vesta has a lot more geology. You can see has impact craters, has these rings there in the upper part of it that are results of a very large impact that occurred on it a long time ago. So, okay, let's go to your last slide, last picture. So this is from an asteroid named Eros, E-R-O-S, and it's similar in shape to Itokawa. It has actually kind of a shape of like a leg bone. If you go do a search for it, Eros is bigger than Itokawa. It actually has craters that you can see are craters. They're round. They're shaped like a crater. And this is just a zoomed in image on part of that asteroid that was taken by a spacecraft that visited Eros. To give you a sense of scale, the larger boulders that you see kind of in the middle left of the picture, those are about the size of a house.
I thought those were like the size of my fist. Wow. No,
those are quite a bit bigger than that. To give you an idea. And then the rest of that stuff's pretty fine grained. Sorry, smaller particles. So Eros is possibly another rubble pile as well, just bigger. in a column. So yeah, asteroids are interesting in that we just don't know much about them because you can only understand so much of them by observing or observing them from Earth, telescopes on Earth. There's only been a few missions that have sent spacecraft to asteroids, and even then, if we get a sample or get pictures of them, that can help us better understand that one particular asteroid, but it can help us better understand just the solar system in general, why things are the way they are. So they're important in that respect. And of course, if we can actually start identifying, all the meteorites we have that don't come from the moon or from Mars, if we could really start identifying where they come from, that would be really, asteroids they come from, that'd be really great too. Okay, very good.